So what we're going to look at now is something called z-score. And to lead into that, I want to go over the example that we did in the previous section, just real briefly. So here's the empirical rule. We have our mean, mu, and then we can go out however many standard deviations we want. So here, this is 1 standard deviation from the mean, 2 standard deviations from the mean, 3 standard deviations. And if something lies within 1 standard deviation of the mean, approximately 68% of observations will lie there. 2 standard deviations is 95, and 3 standard deviations is 99.7. Then we looked at this problem. The average number of popcorn kernels in a large movie bag is 357 with standard deviation 13 kernels. Answer the following. What proportion of large popcorn bags will contain between 344 and 370? What we did was we drew our empirical rule, we drew our graph, then we labeled our mean, and then we wrote out 1 standard deviation from the mean and so on. And then below there we actually computed what these were. We said the mean was 357, and then to go to 1 standard deviation, either way we just subtracted and added 13, so you get 344 and 370, and then we just did that again. Minus 13 this way, plus 13 this way, to get 331 and 383, and so on. Then I asked these questions. Well, let's finish A. So between 344 and 370, so it's minus 1 and plus 1 standard deviation, so that's 68%. And then I said, we asked what proportion will be between 331 and 383. Well, that's minus 2 and plus 2 standard deviations, so 95%. And then same thing for part C. 318 and 396 is 3 standard deviations, so that's 99.7. Then part D, we changed it up. We said 331 to 370, so it's here to here. And all we did was add up these portions here to get our 81.5. So what I want to do is add on to this example, and this will lead us into the z-score. So let's look at part E here. Part E. And I'm going to just keep abbreviating so we don't have to write so much. What proportion of large popcorn bags will contain less than 357 kernels? So I'm just going to say less than 357 question mark. So to do this, we need to look at our graph again. And here's 357 right in the middle. And I want to know what proportion will be less than that. If 357 is right in the middle, you take a guess. Try it yourself and pause the video. So that means 50% will be less than 357, and 50% would be greater than. It's directly in the middle. So here 50% will be less than 357. Okay. The next question I want to ask is F. What proportion of large popcorn bags are less than plus 2 standard deviations from the mean? All right. What proportion are less than plus 2 standard deviations from the mean? So let's come down to our graph and let's find 2 standard deviations. So here's plus 2 standard deviations. So I want to know less than, which is all of this portion. So what's the easiest way to go about that? Well, we know that from here, 357, this is all 50%. So I'm going to come up here and write 50% plus, so we took care of this portion, and then now I just need to add these two. So plus 34% and plus 13.5%. And that gets us 97.5%. So that's kind of what z-scores are finding. They're finding less than a certain value. So where it gets tricky is if I ask you something like this. Part G. What about less than 379? So let's come to our graph and find 379. Here's 370, 383, so 379 is somewhere in the middle here. I don't know where it lies in here, and I don't know exactly how much all this is going to be now, because it's not exactly one of our standard deviations, plus or minus 1, plus or minus 2, or plus or minus 3. So to answer this, I'm just going to leave a big question mark. And this is where z-score comes into play. I'm going to put this away for a minute. And we're going to look at what's called z-score now. So there's going to be a little bit of writing, so just stick with me, but I'm putting a lot of writing on purpose. It's so you can go back and read what we are talking about. So let's write what's happened so far. To this point, our values have been nice. And what I mean by nice is they've been plus or minus 1 standard deviation, plus or minus 2 deviations, and plus or minus 3 standard deviations. Now we have a problem. We need help. It's called z-score. All right, and that's what we're going to define now. Z-score. So the z-score, what it does, and I'm going to write this, I just want to talk about it first. It represents the distance that a data value is from the mean. So what we've been looking at so far are data values that are nice, that are plus or minus 1 standard deviation from the mean, or plus or minus 2 standard deviations. Now in this example, I'm asking something that's in between. So now we need to come up with a way to determine that proportion. And that's what I'm going to write here, something along those lines. Z-score represents the distance a data value is from the mean in terms of, and this is the important one, in terms of the number of standard deviations. And standard deviations we label as sigma. So now this z-score is going to tell us how far away it is from the mean in terms of standard deviations. So I'm going to give you the formulas, and then I'm going to explain more about this z-score. So there's 2 formulas, and they're exactly the same except for one symbol, and you'll see why in a second. So population z-score, and everything we do, there's always a population and a sample. Population z-score, and hopefully by now you're going to know the difference between the population and z-score. Population uses mu, and sample will use what? X bar. So population z-score, and then we'll have a sample z-score. Fairly straightforward formulas here. So it starts out z is equal to, and just watch me for a second and then you can finish writing. So there's a divided sign On top, it's going to be x, so whatever your observation is that you're looking for or that you have, minus the mean mu. Notice I'm using mu because it's the population. And then that is divided by the standard deviation sigma. Then we'll come over to the sample z-score and we'll see it's very similar to this. The only difference is what we're labeling the mean. It's different because we're using sample here. So over here, z is equal to x minus x bar divided by sigma. So same formulas, only difference is when you're finding population z-score, you use the population mean. When you're finding sample z-score, you use the sample mean. All right, and what this represents is it represents how far you are away from the mean. So let's write this. This will help, and I'm going to show a graph here in a second. The z-score, what it does, it allows us to determine the proportion of values less than z. And we have to use a special table to do that. So let's write that out, and it'll make a little more sense in a second. The z-score allows us to determine the proportion of values less than z, and that's a big thing there. Keep that in mind as we're doing this. We're going to be using z-scores for almost the rest of the semester, so we need to get used to this. When we're finding a z-score and we're looking up in this special table I'm going to show you in a little bit, it's telling you the probability that that observation is less than z by using a z table. It's in the book and you can find them online. I will also have to print one out and give it to you. So the way this works is you would find first compute the z-score, then find that value in the z table. All right, so just in general what a graph of this would look like, you could say here is a line and here is our bell-shaped curve that we're working with. And we have our typical, here's the mean, and then 1 standard deviation away, 2 standard deviations away. But here now we're using something more general. We're saying that it's no longer something nice, plus or minus 1 standard deviation away. Now I'm saying z is here. I computed z, that's a z right there. It looks kind of, all right. Now we computed z using these formulas up here. And now when I find z and I look that value up in this special table, it tells me the probability that it's less than z. So when you find a z-score and you look it up in the table, it's telling you the probability that of everything less than that. And you could be on either side of the graph here. Here we're on. We can see that if this is the 50% line, that this value is greater than 50%, or it's better than more than 50% of the observations. Or you can have a z right here, and it's finding this proportion. So if this is the 50% mark here, you know that this value is at least 50% less than all the other observations. All right, so let's go back to our example now and compute that. So I'm going to, it was example 1, part G, and I was looking for less than 379, question mark. All right. Let's come on our table here. And in fact, let's draw a new one because that one's a little out of date now. All right, here's our mean, mu, which is 357. And I know I'm just going to do +1 deviation. I'm just going to write it like that. And we knew that was 370. And +2 standard deviations, that was 383. So the value we're looking for now is 379. So we're just going to put a little point right here. And this is the value I'm looking for. All right, so how do we do that? We find the z-score. All right, and say z is equal to x minus mu over sigma. All right, let's plug in the things that we know. So I know that mu, it told us, was 357. So there's a minus 357. And I'm just doing this part last because that can sometimes be the more difficult part. But it's pretty simple. Then on the bottom is a standard deviation. We were told in the problem that it was 13. Now we need to figure out what to put here. It shows x. That means that you plug in whatever observation that you're looking for there. And in our problem, we're looking for 379, which is this point right here, 379. So that's what I plug in, 379. All right, so this is equal to 1.69. So if we're just looking for z, that means it's 1.69. This is saying, this says 379 is 1.69 standard deviations, so 1.69 sigma from the mean. That's what that's saying. But now what we have to do, now we have to look it up in the table. Look, now we have to look z equal 1.69 up in the z table. And when you're doing this, look at your z table so that way you can find it as well. And let me get my z table here. So you come in here, and this is probably going to be hard to see. But what you do is you come down, there's a long list down this left side right here. A bunch of negative numbers, and then it turns to positive. And then along up here are the hundredths place. This is the decimal place, the tenths place over here. So we're looking for 1.69 in this table. So we come down on the left side till we find 1.6, which is right here on this line. I know you can't see it, but follow along in another table. And then, so I'm 1.6, so it's the probability is somewhere on this line here. Now I come up here and I find the tenths place, which is 0.09. So 1.6 is here, and 09 is here, and then the intersection is 0.9545. So that means the answer to this problem is 0.9545. In other words, 95%, this is equal to 95.45%. That's how much that's greater than 95.45% of all the other observations, which, remember, z-score is looking for everything less than that. All right, one other thing I want to note here is I just want to draw another graph, empirical rule here. So here we have our mean, And so what we've done so far is here we've had plus 1 standard deviation, plus 2. So I'm just going to do the typical thing all the way out to 3 on both sides. So here we have our setup. All of these that we already know how to work with correspond to a z-score also, and this is pretty simple. Here at mu, our mean, z is equal to 0. Over here at plus 1 standard deviation, our z is equal to 1, because z tells us how far we are away from the mean in terms of standard deviations. So if we know we're at 1 standard deviation, that means z is 1. If we're 2 standard deviations away from the mean, that means z is 2. If we're 3 away from the mean, that means it's 3. If we're minus 1 standard deviation from the mean, z is minus 1. And minus 2 here. And minus 3 here. So I'm just trying to put this into a context that we already know. And now what we're going to be focusing on, it's still important to understand that 68% lies here, 95% lies here, and 99.7% lies here. But now our big goal is going to be looking at something in between all these values. That's it for now.